Good afternoon, judges. My name is Charan Bachu, and I'm coming to you from India today. I'm going to try my level best to present, but I hope you don't mind about my difficulties. I'm an incoming freshman at Liberty High School who's passionate about engineering solutions to modern problems. My mention tackles one of, if not the world's largest global issue, climate change. With climate change being such a broad subject, I want to fixate on a smaller component, the gases emitted from smokestacks, specifically capturing all harmful gases, opposed to just carbon. These gases include nearly 45% of total emissions, including nitrous oxide, sulfur dioxide, and of course, carbon dioxide. The exponential rate at which these gases have grown within our atmosphere is unsustainable, which is where my device kicks in. ASK, an acronym for an efficient solution to carbonic acid gas and its environmental desires. I first looked for current methods being developed across the world to improve these surges. Unfortunately, I found that these methods, which consist of carbon capture plants/technologies, have three major limitations: machinery cost, efficiency, and environmental friendliness. Carbon capture plants can cost upwards of $500 million per unit, while others are inefficient, only targeting around 3 to 5% of total emissions, and are hardly sustainable. My device ASK uses multiple novel technologies together, and in turn addresses these flaws by being cost-friendly, sufficient, and easy to install in factories and plants. The missions immediately activate the perpendicularly aligned ASK pods via diffusion. Within each pod being this visual, there is certain content of liquid carbon disulfide dispensed in a vapor format initially. In each device, here's a video of me first. Here's a video of me experimenting with liquid carbon disulfide. It shows the scientific experimentation, and regarding the engineering, that's what I'll be talking to you about. In each device, there are eight pods, of which 5 are always activated, with 3 pods on standby. These 3 pods are activated accordingly through a temperature-dependent algorithm. In this thermal detection system, a spark-for-an A4 thermal camera collects a thermal and pressure input at the stage of pod 5, the last auto-activated pod, and transmits that thermal input to a TNV 4.0 microcontroller, which in turn lights up the given neopixels. The current neopixels are only for display. In real life, the system will collect data in 90-second intervals and use C++ code, the very same as used in elevators. As said earlier, liquid carbon disulfide is dispensed in a vapor form initially. This essentially combines and condenses with the pollutants, thus turning the pollutants themselves to a liquid state. The temperature after condensation right here is negative 35 degrees Celsius. This liquid is transported via pipe systems to large industrial refrigerators located around the premise of the plant, for 2 possibilities: being recycled back into the pod for subsequent condensation cycles, or simply the disposal of excess pollutants. The temperature at this stage, if being recycled back into the pod, is negative 95 degrees Celsius. Up to 30% of my device can be powered by heat flux-based TEGs, while the remaining is compatible to be powered through other renewable or green strategies. ASK should drop the cost less than 1% of current methods, with ASK being only around $475,000 per unit, or to automate an entire factory. My iterations for the device are threefold. First, subsequent cycles. Second, the thermal detection system. And third, my piston system. Just earlier, I said that the liquid vapor droplets condense and combine with the pollutants, which are ultimately recycled back to the device. But what about the initial procedures? Since there's been no smoke that's been collected thus far, there's also none to be recycled. To develop this initial cryogenic substance, I figured that we would first have to kickstart ASK. I expected liquid carbon to be finalized because of its efficiency in abundance, boiling temperature, and compatibility. But due to the honeycomb lattice phenomenon of carbon, I concluded or finalized that I would have to implement another cryogenic liquid. I'd researched liquid argon, liquid hydrogen, liquid nitrogen, and even liquid air, but I found all of them to be ineffective with either the cost or the boiling point. At this point, I circled back and wondered if I could use another gas I'd studied a lot, liquid sulfur dioxide. This was the biggest expected outcome of my project. The reaction between liquid carbon and liquid sulfur yields carbon disulfide, an endothermic reaction at approximately 50 degrees Celsius, assuring the condensation of any temperature, smoke, or plume entering ASK. In addition, I built a piston within my device to lower atmospheric pressure using ideal gas formula and Gay-Lussac's principle. I've designed this piston to be hollow, doubling it as an exit system, and also face several hurdles in determining the ideal diameter. At the beginning of my presentation, I've also talked about the deployment of additional pods to accommodate for higher temperatures of smog or smoke, 3 to be exact. Regarding the activation system of these pods, I'd first believe an app of some sort would be sufficient, where the user would manually enter the temperature, and Bluetooth connection would alert the intelligence support in ASK. However, after understanding that the distance between the user and the device may span several hundred meters in some occasions, I labeled Bluetooth as insufficient. I then moved to a thermal detection system, in which I developed 2 prototypical systems with simple circuit boards before moving on to my final iteration with the Teensy 4.0 mentioned earlier. This was iterated on engineering level. After analyzing the current industrial market, I built ASKH to operate with over 95% of smokestack designs in factories and plants. The industrial market for my device is large, and aims to be even larger in the future. A 2019 study stated that over 90% of factory managers and 85% of business owners find interest in going green, a method to fall under 5% of annual revenue. With both sides of the story shining, I believe my device has a great value proposition and is feasible in today's environment. My device, ASKH, is a carbon capture system that uses completely original technology never been implemented before. And it works for all harmful pollutants, not only carbon. Global warming is an issue of today, as is climate change. But ASKH can be a solution of tomorrow. This is my bibliography, this is some code, this is my logbook. These are some of my 3D printed models. And I want to thank you guys for your time. Have a great rest of your day.